Everybody. So, next up is Book 1, Proposition 3, which says, given two unequal straight lines to cut off from the greater a straight line equal to the less. So this is still kind of like a construction proof. And this one is made almost trivial by Proposition 2. Let's see, so, and we'll see why, because we can just go through Euclid's proof, and then I think once we go through Euclid's proof, I want to do it sort of a second way, maybe the long form way, because Euclid's proof just uses Proposition 2 and everything pretty much falls out. So he says, all right, assume that we've got our two lines, one is longer than the other, so AB is longer than C, and basically what we want to do is we want to cut off from AB some segment that is exactly equal to the line C. So, how do we do that? Well, Euclid says, number one, at the point A, let AD be placed equal to the straight line C. And he says we can do that because in Proposition 2 we just learned how to do that. So, how shall I say, construct AD such that AD equals C, which is, again, Proposition 2 that we just saw. So I think something that's sort of interesting about this proposition is that this is the proposition that says, all right, now we're allowed to have at our disposal non-collapsing compasses. So kind of traditionally the idea with the elements is that all of this geometry is being built up using just an unmarked straight edge, as they call it, and a collapsible compass. Meaning, collapsible means that, like, when you, get out of here, it means like when you lift your compass off of the paper, you lose that angle, right? Like, my compass, modern compasses, they don't. It's a non-collapsible compass. I can put it at whatever angle I like, and it just stays at that. But yeah, the idea is, imagine that we don't have that luxury. Then once you make some line segment or whatever, then, and the moment that you lift your compass, then you lose that sort of like length. But Proposition 2 is the one basically that says that, all right, well, we're going to assume now that we have non-collapsible compasses because we can prove that we could do this. We could do this just using an unmarked straight edge and a collapsible compass. So kind of interesting. So in any case, he says, all right, well, construct off of A, construct some line AD that is equal in length to the line C. So there it is. Here's my AD. AD is equal in length to C. Let's see, I just have like this little mark here that I want to erase. Yep, there we go. Okie dokie. And then I'm sure you see exactly what comes next. What comes next is, well, we're going to make a circle. Construct the circle with center A, radius AD. And then I'll say in the same line, I'm going to let E equal the intersection of this new circle, AAD, with the line AB. So from AD here, with center A, we'll create a circle. There we go. And where the circle intersects the given line, AB, we call that E. And then the claim is that AE is equal to C. AE is the line that we were trying to construct, is to cut off from the greater line and the greater straight line one equal to the less. Did I write this right? To cut off from the greater a straight line equal to the less. Okay, yeah. It's just the funny wording. I was looking at it like at a glance and I was like, wait, that doesn't make sense. So how do we prove it then? Well, and again, I'm just going to try to follow Euclid because it's fairly obvious. I mean, the proof, and I think this is exactly what Euclid does. AE is equal to AD because they're radii of the same circle. AD is constructed equal to C. Yeah, and I'm pretty sure that's all that he does. So we know that AE equals AD. Again, radii is same circle. Or as Euclid justified it, definition 15. But also, C is equal to AE by construction using proposition 2. So therefore, and again, like, us, like with modern, our modern understanding of equality, we would just go, yep, there it is, cool, AD is equal to C. Euclid was a little bit more explicit about that. So basically he would say, oh, okay, well, we have then that AD equals AE and AE equals C, so from common notion 1, AE equals C. C equals, sorry, I wrote this line wrong, probably because I was talking, I should say C is equal to AD. That's the line of reasoning. Yeah, AE is equal to AD. AD is equal to C. Yeah. So yeah, I made this line's a little bit funky, but it's equality, so it's good to go. So, and that's what we wanted. Right, and that's really all that he does. If you wanted to kind of like, you could go through this same proposition and then actually kind of go through all of the pieces of Prop 2. Let's see, so I'll do that really quickly. I mean, just because I think it's fun and it makes the diagram maybe a little bit more interesting. So without going through all of the details of Proposition 2, and I'm just going to kind of do this off of the top of my head because as I recall, Proposition 2 was like, all right, well, take, your line, join endpoints of the two lines. So join the endpoints of, like, say, and you could do either one, B or A, of A to C, and then construct an equilateral triangle of side length AC. And we even extended these out, as I recall. Yes, we extended those out. And then we said, all right, so, and it's kind of like a little bit, the angles are small, that wasn't intentional. Here's the original C. What we're going to do is, we're going to make a circle with radius of C that cuts off on this line right here. Make as much of this circle as I can. It looks like I can maybe do the full thing. Come on now. My compass, I maybe need to get like a better compass. The sharp point on this compass is not particularly sharp, and so it doesn't really stay in place. I have another compass that does have a nice sharp point, but like the angle, that compass, it just makes like the puniest, like the wimpiest little circles. It can only make a circle that maybe has a radius of like an inch maximum. So, okay, so, whoops, come on now, come on, right at the good part. So the idea now is that in the construction of Proposition 2 is that I have this line right here that is on this extended line from the equilateral triangle, and this length from the vertex to this circumference is the length of C, and then now what I do is I make a circle that is a radius centered at the vertex of this equilateral triangle up here with a radius over to this new point, and I bring it down and cut off on this other circle that same length. But we even, like, for the purposes of this proof, we even get it slightly sooner. Oops, that went a little further up than I wanted it to. Because we can take this large sort of this larger circle. So in Prop 2, the large circle would say, all right, well, here's where the large circle intersects this side of this extended side of the equilateral triangle, and then you would make, you know, a circle, basically the circle that we created when we were proving this circle right here, to say, well, here's where it would cut off on right. Is that right? Yeah. Here's where it would cut off. Yeah, good. So, yes. Okay. I'm like confusing myself. Anyway, here's kind of what the larger diagram would look like if you actually went through the steps of Prop 2. Like if you didn't want to just use essentially the shortcut that Prop 2 gives us, which is saying that, all right, non-collapsible compasses are now legal. So this is kind of what the diagram would end up looking like, just to get this point, or this line right here. AE is the line that we're looking for. So yeah, propositions, they build on each other, and just like modern math, the more tools you build, the easier things sometimes end up being. There it is.